of the exact value should you use when you calculate the percentage error?
Percent error can be, there. It depends on how you interpret it. You can just go to rounding percent error off to the nearest integer. Okay. Or I guess hundredth, however you want to look at that. If you have 15.2%, it is okay to round percent error off to 15%.
I know what I meant was, so you have your experimental and your theoretical value.
Right.
And how many significant figures should we, like, when we minus them together, how many significant
When you're doing the calculation, you should be using as much of the number as you can.
Okay.
It's only at the very end which you round off. All right, so but there was another question about finding percent error. So for part A or part B?
Part A, but it's the uncertainty of the percent of error.
Okay. And Austin, your question was about should we have an exact value for percent error for part B?
And I think I was reading something. I think I was reading something wrong. So I'll listen to whatever
Okay.
is going to be said before
All
I
right.
ask anything
All right,
further.
before I get into the math of it, just want to comment on for part B, you'll have your density with some uncertainty in it. You go to a table of densities, whether it's in a book or online, and you'll try to find a value that makes sense for that material. You can pretty much be sure it's not made of mercury because it held its form. And so whatever material you think it is, assume that that book value is the correct value.
Okay.
So that's how you deal with that. So you have 3.17289 plus or minus 0.248. So let's just say that this happens to be your ratio of circumference to diameter. And you want to compare it to pi, because that's what the ratio should be. So percent error, experimental, minus the correct value. I'll put correct in quotation marks there. I do absolute value here. There are some instructors who care about the order. I don't. I take off for other things. But percent error implies that there is an error, which implies that there is an actual correct value. And so you'll compare this to the correct value. That'll get you some decimal, potentially, and then you multiply, then you get into percent form. Now, in this case, pi is the correct value, which I think is the answer to the first question. So when we subtract pi is actually an exact number. I mean, or close enough to it. You can take it out. There are websites out there, the first million digits of pi. So whatever you're willing to type in. So it's close enough to, there is no uncertainty in pi. And so the rules apply. So it's 3.1, so when you subtract 3.172896 minus pi, plus or minus the square root of this uncertainty, the 0.24 squared plus 0 squared, which is just the uncertainty of your calculation. So you'll end up with, the numerator is just your main number minus pi, and then it'll be that experimental, that'll be the uncertainty. The denominator, you're dividing by pi, so you're basically multiplying by a constant. And so you'll end up with 0.031 something, plus or minus 0.2489 something. And when you divide by pi, since it is a constant, technically pi plus or minus 0, then it's 0.301 yada 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 over pi, plus or minus 0.03. Let's try to be somewhat consistent with my made up numbers. Plus or minus 0.031 over pi times the square root of, well, my relative uncertainties. So 0.2489 whatever over, I guess the difference 0.031 squared plus 0 over pi squared. I'm going about it the long way, but it still works. So you have your main number here, and this is on your uncertainty. This obviously is 0 there. You just end up with 0.031 over pi times that uncertainty, which carries over to here, which carries over to here, 248 over 0.031. Those cancel out. So in essence, all you do is you have your main number divided by pi, plus or minus that uncertainty divided by pi. Did that address your question, Max?
Yeah, I got it.
Okay. Was it far more than you asked?
No.
Okay.
So I have one more question.
Yeah, Kyle.
When you're finding the volume and the area, do you need to include the uncertainty in that too?
Yes.
Okay.
I want uncertainties for, let's say, all the calculations. I mean, yeah, uncertainties throughout that.
Okay.
That's what makes it a fun lab. Just wait till the projectile motion lab. It'll be a dream come true. Other questions at the moment? Precious.
When they say which of the two variables that were measured contributes more to the uncertainty in the calculated ratio, does that mean of the two variables, which one has the higher uncertainty?
Not necessarily. It depends if you're adding, subtracting, or multiplying, dividing.
Okay.
But the uncertainty, if I'm multiplying or dividing, then my uncertainty, I basically have two fractions here. If I'm adding or subtracting, I'm dealing with absolute absolute uncertainties. And so I could get away with whichever one's bigger for adding and subtracting, but multiplying and dividing, you need to look at which has a greater contribution. Other questions? All right. Questions about things other than the lab? All right. I'll pick up sort of where we left off. Yep, it is recording. All right, so we got the big four properties of linear motion. We have position, displacement, velocity, and acceleration. So position is where an object is with respect to the origin. And I'll put in parentheses here, 0. If it's a number line, you generally don't call it 0 the origin, even though it is. Two-dimensional system, we have something, actually 2 dimensions and beyond, we generally have something called an origin. Displacement, where an object is with respect to the starting point. Which brings up the question of what exactly is the starting point? Is it from where the problem starts, or is it from the moment just before? And so that gets into two different types of displacement. If we're talking about overall displacement, which is the one that's implied. If I just say displacement, I'm talking about overall displacement. Overall displacement, the starting point is at the beginning of the problem. So starting point at beginning of problem. Now, generally, you have a freedom when you're solving a problem of making it. You can set up your own coordinate system. You can make the origin anywhere you want. It is usually convenient to make the origin and the starting point the same place. However, the exercise we're about to go through, we're not going to do that. Velocity. Questions to hear before I just keep going?
Will we ever use instantaneous displacement?
Yeah, implied when we deal with velocity. So velocity, how fast and in what direction? And acceleration, I guess time rate, that's the word time. Let's see if I can actually spell it so it's readable. Time rate of change of velocity. Velocity could also be labeled as the time rate of change of position. Of change of position. Which is just displacement divided by time. This is all just vocabulary at this point. So what I want us to concentrate on now is sort of trying to be able to figure out when is it positive, negative, or zero. So the sign, S-I-G-N, in other words, plus, 0, or negative. For position, it depends upon what side of the origin you're on. So it is positive if on positive side of the origin. All right. So I'm about to walk back and forth in front of the board, a one-dimensional problem, or at least a simulation of it. And I'm going to make that the origin right there. Make that 0. And because so if I'm at the origin, my position is 0. Something you need help reading?
No, I'm good now.
Okay. Now there's going to be some parallax here because I think Mario and Austin probably have the biggest slants to the angle here. If it looks like I'm about at the origin, then I'm at the origin. I don't want to fall into this max impression say I'm at the origin, you say I'm on the one side, and you say I'm on the other side. I'm not playing that kind of subtlety here. So we need to know which is the positive side, which is the negative side, so I'm going to make positive side over here. And the way this game works, in unison would be absolutely beautiful. I'm going to say my position is, and then your response is either positive, negative, or 0. Not all three of them, just pick one. Pick the correct one. So right now, my position is
Positive.
That was nice. My position now?
Positive.
Position now?
0.
My position now?
Negative.
My position now?
Negative.
All right, that's the way the game's played. Any questions about the game at the moment? The exercise, activity, whatever you want to call it. Displacement, it's positive if on positive side of starting point. I've already established positive is to your right. I'm going to make for this exercise, this is my starting point right here. So right now, oh, people are still writing, give people a chance to catch up. All right, so right now, my position,
Oh, your position's.
yes, and this is why it gets more complicated because there's more vocab words I can throw out here. All right, so let's try that again. My position,
Positive.
my displacement,
Zero.
all right, there we go. My position,
Positive.
my displacement,
One.
I heard something other than negative.
Oh, I thought you said your displacement. I just said one because you moved one.
Just positive, negative, or zero. I'm on the negative side, it is negative. My position,
Negative.
displacement,
Negative.
all right. As I start to add more of these, the faster the response would really be helpful. It's only so slow I can go, although I can rewind. Velocity cares about which direction you're going in, so velocity is positive if moving in the positive direction. And obviously negative if it's moving in the negative direction. So right now, my position,
Positive.
kind of threw people off there. My displacement, my velocity,
Zero.
all right. Position,
Positive.
displacement,
Negative.
velocity,
Negative.
velocity,
Negative.
position.
Negative.
Yeah, that was, I'm glad you were answering for just before I stopped. All right. My velocity,
Positive.
position,
Negative.
Positive.
now it is, and, wow. I have to go a little bit faster too. All right, so rewind. All right, so my velocity
Positive.
is positive. And this is an instantaneous displacement because I was there, now I'm here, my instantaneous displacement was in the positive direction. My displacement,
Negative.
all right, not everyone was convinced on that one. Velocity,
Positive.
displacement,
Negative.
position,
Positive.
it is now, all right. Any questions up to here because we're about to get to the tricky one? We can look at acceleration a couple different ways. Way number one is if you're speeding up, velocity and acceleration have the same sign. If slowing down, they're opposite signs. The other way of looking at it deals with forces, and I know we haven't really talked about forces in here, but just think of a push or a pull. If the net force is positive, acceleration is positive. If the net force is negative, acceleration is negative. So let's see how that plays out. So I'm starting right here. My velocity is 0. If I start moving in the negative direction, what will my velocity be? Because velocity cares about which way I'm going, so if I go in the negative direction, then it's negative. So negative velocity. So I went from 0 to some negative value. Did I speed up or slow down?
Speed up.
So my acceleration therefore was, if I'm speeding up, they're the same sign. And that's the biggest hurdle here, is so many people are convinced that positive acceleration means speeding up. No. Not the case just then. All right, so I start here, I start moving in the negative direction, so as soon as I start moving, I have negative acceleration. I'm starting here, and then I start moving in the positive direction. My acceleration at that moment that I started moving, I'm moving in the negative direction, and then I slow down.
Positive.
I'm moving in the positive direction, and I slow down. Negative acceleration, in that case. Now let's think about it in terms of forces. I'm standing here at rest, and suddenly I start moving in that direction. Which way would I have to be pushed or pulled in order to do that? Yeah. If I'm here and I start moving in that direction, something has to be pushing me or pulling me in that direction. So therefore, the force is in the negative direction, acceleration is negative. If I'm moving in the negative direction and then I stop, which way does the force have to be applied to me in order to stop me? Acceleration is positive as I slow down. So this whole idea of the same sign comes from the fact that if you get pushed in the direction you're already moving, you're going to speed up. If you're pushed opposite the direction you're moving, you're going to slow down. Now the speeding up, slowing down works really nicely, but some people get really messed up at the transitions. So as I'm moving along, I stop and then I go back in the other direction. At that moment that I am stopped, so moving along, that I can't go from negative to positive velocities without going through zero, so I have to stop at some point. So as I move there and back, oh, the exception, unless there's a rip in the space-time continuum, which is outside the scope of the course. So at that moment that I'm stopped, what was my acceleration? I heard a positive and a zero. Actually, I heard a zero and a positive.
Zero.
Another vote for zero, another vote for zero.
Zero.
Any votes for negative? Moving in the negative direction. Stop for just a brief instant, then move back.
Are you talking about the moment when you stopped?
Yes.
Zero.
Going to be positive and then stop.
All right, so we got two votes for positive. Jesse gave a nod of approval there. Not that you need external validation, but I think.
Acceleration.
All right, so let's think about what acceleration is, because that's an important question. Acceleration, instantaneous acceleration, dv dt. Let's go sort of macroscopic, just why not? Average acceleration, change in velocity over change in time. If acceleration is zero, there's no change in velocity. So you're stopped at a stoplight. Your velocity is zero. If acceleration is zero because you are stopped, that means your velocity won't change. And what's the implication? If you're at a stoplight, stopped, the light turns to green. If your velocity doesn't change because acceleration is zero, what's going to happen to you?
Constant.
A constant what?
Speed. Zero.
Yeah, you'll never move. And I think most of us have experienced the fact that we have been at rest at some point and then not at rest. So it is possible to have acceleration and be stopped. So, you were right. It is positive. From a force point of view, if I am being at the turnaround, in order for me to stop and move back the other direction, something has to be pushing me. Basically slowing me down and then pushing me back.
So
Mario?
the first derivative of position gives you velocity, then the second derivative gives you acceleration.
Yes. All right, we got 4 things now. Ready? Here we go. Position. Displacement. Still considering this my starting point. Velocity.
Zero.
Acceleration. Because I'm at rest and staying that way. All right, so I just started moving. My acceleration. My acceleration now.
Negative.
I heard 2 different things there.
No, zero. If you're constant velocity, you're on zero.
Yeah, it was my attempt at constant velocity, yes. After I started moving, I'm pretending that I'm moving at a constant velocity here. There's no change, therefore acceleration is 0. My position,
Negative.
displacement,
Negative.
velocity, my acceleration at that moment.
Negative.
Negative.
They were negative. Because in order for me to, I'm moving in this direction, in order for me to stop, basically something has to stop me, so pushing in that direction, pushing against me, and then pushing me back. Pushing in that direction the entire time. Or I slowed down, so the signs were opposite. My velocity was positive, so my acceleration has to be negative. And then I started speeding up. Velocity is positive, velocity is negative, acceleration is still negative. Here's another way of looking at the exact same thing. So I'm moving in the positive direction, I stop and I move back in the other direction. So I have time, velocity. But that's seconds, so that's meters per second. So 0, 1, 2, 3, 4. My velocity, we'll just say I was cruising along at 10 meters per second. You know, not world record pace, but close to it. And then I slow down at, let's say, then I'm going 5 meters per second. So from here to here, what's my change in velocity? Then 0, so what's again my change in velocity? Now I'm at -5, I'm going in the negative direction here. What's my change? -5. Change is always final minus initial. It's this minus that. My change again? Now this is change in velocity, it's not acceleration, but change in velocity and acceleration are always the same sign. So my acceleration is constant here, because my change in velocity is constant for the same time increments, or close enough. But I'm slowing down, slow down, and then speed up. And acceleration is the same throughout the whole thing.
What is WRT? What's that?
Oh, here?
Yeah,
WRT, oh, with respect to.
with respect to. Thank
Yes.
you.
Shorthand notation from former math professors, just because we don't feel like writing. I think you're ready for the ball problem. Now, ordinarily, I'd have you sort of break into groups, but feel free to talk to people from a proper distance. Don't talk to someone on the other side of the room, unless you walk over there, please. So, the ball problem. Have any of you watched the video already? You did, and you watched the answer already?
Yeah.
Okay, so if you already know, if you remember it, you already know the answers, and you're working with somebody, just sort of let them struggle a little bit. Or if you're, army of one and not working with anybody, then just sort of sit there and smugly go, yeah, I know what the answer is. Ground. You throw a ball into the air. It goes up and then it comes back down. It's supposed to be a one-dimensional problem. I drew a little split there just so that you can see that there's motion there. in reality, it's just basically doing that. It goes up and then back along the same line. I'm going to define 4 times here. A, time just after ball leaves hand. So as soon as the ball leaves the hand, that's when time A is. Time B. B is the time when ball is at the peak. C, the time when ball is at same position as it was at time A, but on the way down. So at time A and time C, the ball's in the exact same location, just at time A it's going up, time B, C it's going down. And then D, time just before ball touches ground. All right, questions up to here about what the problem that's being laid out so far? I need to do a couple more things before I set you loose.
So where are we defining the axis for positive position?
That's the next thing I need to do. I'm going to let the ground be my origin. Ground is 0. And just so that we're all on the same page, ordinarily in a problem like this, if this were like a test, and I was asking actually specific information, you could determine what's positive and negative direction, but just so that we all are working towards the same answer, let's make up positive. And I think that answers your question, Austin? Okay. Any questions about the problem before I state exactly what I want you to do? Okay. Recognize that at time A, ball is here, time B, time C, and then time D. But the ball also exists between those times. So what I want you to do is tell me what is the position, displacement, velocity. Displacement is overall displacement. Velocity and acceleration are instantaneous. It's implied in the language. So I'll use x, delta x, v, and a. When are they positive, 0, or negative? And in terms of notation, I'm borrowing it from math. If, for example, one of these happens from A to B, including A and B, you would write that as A, B. So this is from A to B, including A and B. A to C, from A to C, including A and C. So you don't have to write B in there, since if you write A comma C, then B is in the mix. So includes endpoints and points in between. If it happens from A to B, including B but not A, parenthesis next to A, a bracket next to D. So this is from A to B, not including A. I guess including B, but not A. And so if I, let's say, parentheses AD,
B and C. Is it gonna include B and C on?
more than just B and C,
Everything in between?
everything in between A and D. Not A and D though. If something happens at just point A only, then just write A. Or if it happens at A and D, A and D. One other piece of information, just to avoid potential confusion later. The problem starts just after ball leaves hand and ends just before ball touches ground. Awesome.
So does that mean that, is A considered the starting point, or
Yes.
is the hand?
Well, technically A is the time when the ball's at the starting point.
Okay, all right.
If you look at the old test, some of the earlier tests, I got sloppy with the language and I just said A was the starting point as opposed to technically A is the time when the ball's at the starting point. All right. Take about 5-10 minutes. Try to do this on your own or with someone near you. And then we will talk as a group and then we will do a test level problem.
The last notation, AD without parentheses,
So this would be
that's excluding A and B. A
not,
and B.
not including A and B.
And the last one? that
It's
was
just point A and just point B. Or time A and time B. Nothing in between.
Yeah, I don't think you're.
So this and this would comprise the entire set. Because this is from AD, not including A and D, and that's the points A and D.
Did you say that, oh wait, never mind. That's on the board.
You want a table like that, like you put in your.
When I present the answer, I'm going to use the table like this. There are other ways of presenting it. There's a PowerPoint that's posted, that I'm pretty sure I posted for this group, where I talk about 4 different ways of expressing the final answer. So if you have a better way you wish to express the answer, I'm open to that. But I plan to, as a group, present it this way, and then I'll talk about other methods of presenting. Awesome.
I just wanted to see if some of the assumptions I made here were right.
what they were, right?
Should be positive. Yeah.
Because in the position, so when you say the ground, the ball says on top of the ground, so is it?
The problem didn't just for touch it.
So then it was.
Right, you're right here, that's right. That's right, that's all. Wait. Yeah, that's right.
So this is all?
Yep.
But once you hit, since this is the deal, we're going to start going to go past.
Which spreadsheet software did you say you use?
They use OpenOffice.
OpenOffice? I've been messing with things up.
It's a straight line, not the.
One thing that Excel has that is easier than OpenOffice is if you want to do programming. Programming in Excel in basic, it's simpler than programming in OpenOffice.
Yeah, well, I've never touched that function before.
Okay. The commands are still the same. And there's some other eccentric differences you can get used to. I think it's Excel, every time you open up, one of them, every time you open up a new spreadsheet, it basically opens up the program again. And the other one, you have the base program and then extra, bringing up extra spreadsheets does not take up that much more memory. So there's a lot more memory if you have just one, less memory if you have multiple. Right now, can't remember which is which.
It doesn't speed up.
Well, I would think it was slowing down because you're pushing it up.
Yeah,
And then
I'm
it's,
going from A to D. It's
you gotta, from A to B to slow down, and then from B to D to speed it up, right?
No, it's constant.
So,
It's on the first, second, on the first, right?
That's the thing.
It doesn't speed up or slow down. Tiny from. It's the one that comes up.
It's a zero.
It is there.
This is, it's
So
not
from A to
that,
B.
it's 100.
It slows down, going up, and then at B it takes zero, and then from B to B
It's
it's speeding up.
constant. It's constant. Why is it constant?
Not a constant, yeah, I'm pretty sure it's speeding up,
Because.
because gravity comes down.
That's what point does it go constant though?
Yeah.
Acceleration,
From,
velocity?
as soon as it gets to.
direction.
It's gonna stop.
So from,
Before you
from
can
A
go
to,
in any direction, you
A
have
to
to.
B.
Zero.
So with the,
Negative.
with
From A to B,
the
it's slowing
velocity,
down.
with the velocity from A to C, it's positive, right, not including C. But then
Really, because I
at
would think,
C, it's zero. Or, excuse me, at B.
at B it's zero, and then from B to D,
Oh, this is the final.
Hold on, I'm looking, I'm sorry, I'm looking at my display,
It's gonna be
never
the
mind.
same.
So from A to B, not
It's the
including
same
D,
sign.
it's positive.
I thought it was
And
negative.
B, huh?
But when does it stay the same?
Cause it's moving
Yeah,
in
you
a
do it
positive
in
direction.
consideration.
Yeah.
So with velocity, if it's
Is it all
moving in
going
the
the same
positive
speed?
direction, it's positive.
I was gonna say
If it's stagnant, it's zero, or if it's moving in the negative direction, it's negative.
You're
Every
right.
single time it's gonna go slower.
Oh.
So.
That's the issue,
Yeah, at B to zero, and then from B to D, it's negative.
negative.
Cause then, once it's going down, it's gonna go faster, and then the velocity is negative, and so it'll be the opposite, right?
Those things, that makes sense.
Okay, so.
Yeah, that's good.
Over time, I'm seeing what's going on.
Yeah, because you have the force.
Yeah.
going down, so that means.
It's a classic mistake to this average.
Yeah.
I'm not going to.
If you did this one. There's that screen, everyone in the class get acceleration right the first time. Yes.
No.
Just slow down. I hope so. I will continue with non-actual peak. That's what I got.
They are backwards.
Yeah.
So,
You want the ratio for these, for these,
Starts right after all these.
all these ones,
And in between.
and in between.
So for example, positioning. I said up was positive.
as soon as it leaves the
And down
ground,
is zero. Wait, also opposite side of the entire term.
Oh, here, what I was thinking is, what is this, this is.
So you're right,
This is the,
you are, 'cause as soon as
this
the-
A and it's positive for the first, for just
Yeah.
this position. And then,
Yeah, I think I'm just a little bit concerned.
If you look, it sounds like you're just looking at.
You check mine.
A, B, C, and D. It's A, between A.
Just tell me which
C,
one's wrong.
B, C, C, and D, and G. There's actually 1, 2, 3, 4, 5, 6, 7 different.
A, as you know, he said going up is A. So.
Time intervals?
From A
In
to
a sense?
Like, I'll just tell you without explaining it.
You can explain it too, I mean,
Yeah, but it's.
Listen to the explanation.
Much bigger, no? Because that's why I was trying to separate.
This whole thing?
That's why I choose that, and because if not,
Because
Eh,
remember when
let's say, these are the two,
It says going up is
all
positive.
another, I can, that we can.
So that's what leaves it.
so before he was like, this is your, this is the ground,
No,
and
alright, so
then
position
this
is
is all
positive.
positive, this is
So
all
you would write
negative.
here.
And then, but
Square
then
bracket,
there,
based on the D.
the ground is
Close
here
square
and
bracket.
everything there is positive.
And
So
these two.
therefore, like, all the positions.
So you don't need a lot of space. That's one of the reasons why I was.
So you get it.
Yeah, no, I do get that. We were arguing that. We were like talking about considering that as a zero, because he did say that was a zero. And I was telling him he can't be negative until it reaches that.
Yeah,
So
so
these
for
are-
position,
It starts at
for
point A,
position, it can only be
stops at point D,
positive.
so.
And
Yeah.
but for starting point
That takes into
for,
account everything.
Displacement velocity.
But then, where you write the other one,
Oh,
where you write the other.
okay. So are these right?
Not quite.
Because for these, we did consider that as a starting point.
If, let's say that, if I answer that, I answer just this triangle. This piece of the,
Yeah, positive, zero, negative.
Trajectory.
oh, the trajectory, I'm sorry.
Except position's positive also along here.
yeah.
Yeah. but the position is positive
I think
all
this
the
is not
time,
including A,
Right.
because that A
So
is
you
like at the origin, like at the starting
Alright,
point.
so after we put
that-
things
that's
in brackets,
technically
I'll
zero.
give another.
But isn't that when it says it doesn't start till it leaves the hand? So as soon as it leaves the hand,
But he was like,
That
at
means
A, it's
I'll
at
set
the
up a grid.
origin.
ooh, okay, yeah.
That's why,
Good
that's
idea.
why this is zero, because if A was not,
Yeah, that's why that's zero, because it's, so it's from A to C, not including
and
A.
A and C are zero.
Ah. And then that's right, it's from C to D,
Yes,
not including C, says that's a zero.
yes.
Ooh, nice. Okay, so all those are positive, and it includes all of them, right? So if I rewrite that as that, that's correct, and that's not.
Yes.
A to D. Okay, and then what about velocity?
And then
And
for,
velocity,
Alright,
so it just
You have
depends on
C included as
position,
positive
but
here
at B
because it's
is
square
zero
bracket.
because
You have
it's
C
at
included
P.
as negative
At B,
here.
okay, so I got
Yeah.
that, for B is a P, and I probably don't wanna include that, right?
Yeah,
That's a zero as well, or is that correct?
yeah, that's correct.
Okay,
Yeah,
and
yeah, I
then,
don't think I know the answer.
you explained these pretty well, so.
Yeah, I think this is correct.
These two, the bottom two?
Oh, wait. Well, the acceleration is the acceleration of gravity, and gravity only acts downwards.
Yeah, sure, if you're gonna do it this way, I'll do that.
So, like the acceleration
C
is always
is not included, because C is included here. Positive is
So
still above.
from A to D, not including A,
Ground is the origin.
no everything is
From the starting point, so this is
gravity.
starting
D
point.
is
it's making us slow
just
down.
before it touches the ground.
So-
Right. Or is it staying constant? Oh, it's staying constant.
Gravity is just acting downwards.
The ground itself. It never actually, it never makes it there during the.
So it's from A to that negative.
From A to C is, this is
Yeah,
the, or
it's-
this is the starting point, this is from A to C is positive,
Uh,
including C.
I'm gonna leave that to
Yeah.
compare.
Yeah, because,
I got that wrong this time. So I'm
positive
like, what?
is positive side.
Which one, the acceleration?
Yeah.
So it's still
That one's
positive side.
confusing.
So it's still above, but
It's like you gotta think backwards.
So it's still positive side.
Well, I thought it was zero because obviously you go up and then once you go down, it's gonna reach the same point. So that's why, for the pace. Yeah.
And the A to D here, A to C, close bracket.
Yeah.
So that is always positive, right? Because it's all on top of the point.
In order for it to be negative,
They
they
have to
have to
be
break through the.
right for the ground, yeah.
Yeah,
Well, that's
I
what
see.
happens.
Yeah.
So everything above the starting point is positive. And then for the, displacement from A to C, because it's all above the starting point,
But do you
including C.
No, I don't think you include it because that's a zero.
You gonna include C?
Yeah, remember how he was doing that problem where you walk and then you walk back and if you're back.
But it's right above, but it's right above the origin, not past the origin. 'Cause it says the time, just
No,
after
this
the
is just
point.
Displacement.
I'm sorry, the starting point.
Displacement is considered the starting point. So like you start here and you go back to the starting point, displacement is zero. You're
Okay,
exactly.
okay, that's right.
Yeah, that's what
Okay, I see what you're saying.
All right, let's take a look as a group, and I know not everyone's done, but we need to reconvene. And the the huge number of people watching this video are gonna wonder, am I just gonna stare at the board the entire time? All part of the dream. The most prolific, unwatched creator of YouTube videos. Rarely watched. All right, so position, because the ground is the origin and the ball never gets to the ground. Because again, problem ends just before the ball touches the ground. It is positive the entire time. Because up is positive and position cares about where it is relative to the origin. So this is from A to D. Not there, not there. It's positive the entire time. Another way of expressing the same thing is in a chart like this, where it's just positive the entire time. And the advantage of the grid form like this is that it emphasizes the fact that it is the 4 points that I defined specifically, but it also includes everything in between. All right. Any questions about the fact why the position is positive the entire time? All right, displacement. Displacement cares about where an object is relative to the starting point. Well, the starting point is at point A because starts just after ball leaves hand, and time is A is the time just after ball leaves hand. So the displacement is 0 at time A. At time, and then at C, it's at the exact same location. So all we've basically done is, it's in a sense, the displacement versus position, it's just changing your coordinate system. So position cares about here, displacement cares about here. So displacement's positive when it's above there, it's negative when it's below there. And the reason it's positive when I say it's positive above there is because I said up was positive. So it's positive from A to C. And then negative from C to D. So over here, it is 0 here, 0 here, positive from A to C, not including them, and then negative afterwards. Another thing this chart illustrates is the fact that you cannot go from positive to negative without going through 0. There is one test where it did happen because I misworded one of my definitions, and in that situation I had much more flexibility in what the correct answer was because I screwed up. But when you go from positive to negative, you need to pass through 0. Velocity cares about the direction you're moving. Positive one going up, negative one going down. At B, it's at rest, by nature of the fact that it's at the peak. And so my velocity starts out moving up, and not including B for positive, and then all the way down, B to D. So it's positive before that and negative after. And then acceleration. As it is moving upwards, is it speeding up or slowing down? So the velocity and acceleration need to be opposite signs. So as it's going up, acceleration has to be the opposite sign. As it's going down, speeding up or slowing down? So it's the same sign. And that leaves this pesky one right here. But if you think about it, if I'm going from, so up is positive, so if I have going at 10 meters per second here and at negative 10 meters per second there, my change in velocity is negative. So that's negative as well. Potentially easier to think of in terms of force after it has left the hand. And remember, no Jedi powers here. After it has left the hand, what force is acting on the ball?
Gravity.
I'll nitpick that one later. Yes. And which way does the force of gravity act?
Down.
Towards the planet. And down, its force of gravity is acting on it the entire time. Downwards, which is negative. I saw some people still working under this idea that when it stops, the acceleration is 0. That would be a really cool effect if you could do that, because if acceleration is 0 when at the peak, that means there's no change in velocity. So the ball, you throw the ball in the air, it stops and then stays there hovering. However, I would contend, if that's the way physics worked, we as a species would have exterminated ourselves years ago. Imagine you jump into the air and never come down. All right, questions to hear? All right, so let's add a little bit of excitement to this. Let's graph it. More specifically, let's sketch a graph. Graphs, plural. And so when I say sketch, this is not a precise thing. We're doing this mess. Oh, Roberto.
Yeah, why in this graph okay, no, you say AD, no, okay, sorry.
All right.
Yeah.
So position versus time. Velocity versus time. Acceleration versus time. Now there are a couple of characteristics here. One, whether it's positive or negative, in other words, above the time axis or below the time axis, needs to match what we have right here, or what we have over there. The other thing is that velocity is the slope of my position graph and acceleration is the slope of the velocity graph. So all those things need to be in common. Also, other than potentially at the endpoints, because the problem begins and ends, it should be differentiable in between, no sharp points. Now this one, it's a little bit easier than the one we'll do next. So it starts out, I know the ground is 0, it stays positive the entire time. I'm just putting a little dotted line here, just as a placeholder. This in theory is the peak, so that would be point B. That would be A. That would be C, and then that would be D. My recommendation is that on a test, use a pencil the first round through, unless you're feeling really confident. Velocity, I know, is positive, so, and it's 0 at B, so we'll at least get that down. So that's my point B right there. It's positive, and it does match what I have here, because since this is the slope of that, it is indeed positive from the start to the end. So my slope starts like that, my slope gets less and less, so my velocity starts high and then goes to 0. And then over here, my velocity starts at 0 and then becomes more and more negative. And then acceleration needs to be the slope of that. Now, I drew this as a straight line, so my slope would be
The same?
as this? Or you saying constant? Yeah, it would be constant, and yes, that's what I'm going for. Thanks for the mind reading. And that matches what we have right here. It's negative the entire time. And so this matches what I have over here, or that, and that. And they are consistent within themselves. So this is the slope of that, seems close enough, and that's the slope of this. So at this point, I could go ahead and connect that. And because acceleration is constant, this should be part of a parabola, and this should be a straight line, and that should be flat. A slope line, I should say, flat. All right. Questions before we tackle the test level problem? Or, all right, any questions? Want to stretch legs, come back, feel refreshed, raring to go while I write up the problem?
George, you put this, the acceleration like positive, was not negative all the time?
Acceleration was negative all the time.
Okay, I saw that you put it above the axis in that graph.
Oh, no, my axis was here, and then I drew my acceleration down here.
Okay, minus G then.
Yeah, that's the trouble with two straight lines and using the same color ink.
Okay.
Oh, didn't find the origin. So the problem starts, well, at time A, because that's when the box enters the problem. The box is already moving to the right. I guess here's the wording. A box slides toward a wall to the right. It is initially on a frictionless surface, but experiences friction about a third of the distance towards the wall. The friction stops before the box touches the wall. So that's what this symbol right here is. This is the symbol for technically the coefficient of friction, and that it experiences friction starting at time B and ends just before time D. So both ways. So there's friction in this region right here. The box hits the wall, which moves back some before bouncing back towards the starting point. It is going over the friction section of the floor. The second time, the box stops, which coincidentally is the origin. So it stops at time I, and the box is at the origin at that point. So here's what's happening is that box is sliding towards the wall on a frictionless surface, then it hits friction, and then it's frictionless again, it hits the wall will deflect some, and then this will bounce back across frictionless surface, hit friction, and stop. Questions about the problem? Yeah, Mario.
There's no friction on D to E, just
Correct.
E to D? Okay.
Including B, but not D.
Okay.
And the problem, I didn't have this notation here. I had the line representing from B to D, but in the wording here, B time box first reaches the friction section, so B does have friction, and D, the first moment the box is not experiencing friction, so D is not included. Roberto, you got a question in the comment?
Do you want this paper or?
No, that was for your own edification.
Alright, so at point C, what is that word after box?
Passes. Time box passes the eventual stopping point, but while moving to the right.
Alright, thank you.
All right, so let's do this. So I guess I didn't finish that chart. This is 0, negative. And over here, I have 3 different ways of expressing the exact same answer. On a test, I'm not going to ask you to do all 3 ways. I think the last one I gave 4 different ways of expressing it and just said pick one. Occasionally there's a student who does more than one, which is fine, except for the fact that the student contradicted himself. So that's always fun to grade. Now it's possible the student started on one section and thought, oh, I really don't like this, let me do a different one. If you do something like that, just say, pick this one or ignore this one. Big X to the one you don't want me to look at. All right, so let's start out with position. And something like this, I find it usually easiest to start out with, where is it 0? Where's position 0? Okay. So I and C, doesn't matter the order in which you do it. Here, this is 0, and that is 0, and potentially go for just absolutely stunning visual effects. And then down here, we can shade this in. If you already know that you really hate one of these presentations, then just don't do it. Do the others. All right, so where is position positive?
Not including C or I.
From C to I, not including C or I? So you're saying everywhere in between these two. Now, the advantage to the first method, in my opinion, is that it doesn't take up much space. It's conciseness of language. The disadvantage is Some students have a difficulty knowing have they covered everything. They have a bracket here, they have a bracket there. They didn't mean to put a bracket in 2 places, but they did, and suddenly you have some point in this which is both positive and negative and 0 at the same time. I've gotten that occasionally. This one, you're less apt to leave something blank. Advantage of this one is you're practically doing the graph already. I know it's going to cross 0 here, and it's going to come over and hit 0 again. All right, and negative?
A to C, not including C.
A to what again?
A to C, not including C.
So, negative, negative, negative. Questions about position? All right, displacement. Where is it 0?
A.
All right. 0. Where is it positive?
Everywhere else, A to I.
So, beautifully shaded. Now, if you are doing this method right here, or the one, it used to be I gave only one way of presenting the information, and you're supposed to basically use that notation. If something is blank on some case like that, if this is blank, you need to make sure it's explicit that you're intentionally leaving it blank. So either cross through it or put NA for not applicable, something like that. Just so it's clear that you didn't just skip over it. All right, velocity. Where is velocity equal to 0?
Just F.
Just what?
F.
F?
Or, figure out not first.
Any?
I.
Yeah, F and I. Did you say I?
No.
Okay. I'm sure the rest of the group appreciates you giving them a chance. All right, so this is 0 at F and I. Where is it positive?
A to B, not including B.
What happens at B?
It hits friction, so it slows down.
But we're doing velocity now.
Oh, not really.
Oh, okay. Where's velocity positive? Wait, say it again, sorry.
A to F, not including F.
All right. So A to F, not including F, because F is over here. So oh, and this is all positive. Like that blank. And negative?
F to I, not including both.
All right. And then down here, it is 0 at this point, and then positive before, negative after. And then acceleration. Right. Where's acceleration equal to 0? Okay. Is it A and B or A to B? At A.
A to B is no friction on this.
Yeah.
Constant movement.
So there's nothing slowing it down here. There's nothing to cause a change in velocity as A is moving along here. It's not until it gets the friction that it's going to suddenly start slowing down. Or will suddenly or gradually start slowing down. It'll start slowing down. So A is 0. From A to B is 0.
But not including B.
So includes A but not B. So once it hits the friction, is it going to speed up or slow down?
So it'll slow down,
So
negative.
the sign has to be opposite.
B to D.
Including D or not?
No.
All right, so it's negative from including D, but not D. And then what about happens at D?
Speeds up. There's no friction, right?
What would cause it to speed up?
Well, there's no more friction.
Right, but with that, does that mean it's going to speed up?
Yeah, there's nothing to make it speed up, so it's gonna be the same.
Yeah, so it's 0 again. And also another way of looking at it, once you recognize that it's not negative at D, there's only one choice here. It's got to be 0. You can't suddenly go from negative to positive without passing through 0.
E to F, not including F is 0.
But you said D to F?
No.
But at E is the last moment before it touches the wall. So the boxes change. All right, so you have E, then it touches F, bouncing back, and as soon as it separates, you're at G. So while it is touching, so first off from D to E.
0.
Okay. And E, it's not touching the wall at E, because it says in the text. From E to F. Is that negative sign with a question mark over it?
Well, if you slow it down, so it would be the opposite.
It would. All right, so it is negative. Have more confidence. Even if you're wrong, just say it with great confidence. How about F to G? We'll skip F for just a moment. F to G.
Positive, because it's taking an impact. Once it hits it, doesn't it bounce
Well,
back?
wouldn't
It does bounce back.
Wouldn't it be negative, because if you think about it, the force is forcing it back that way?
Or look at it from the point of view from F to G, it's speeding back up again. And so the sign has to be the same as velocity. So what's happening at F?
It would have to be negative then.
Yeah, it would. Primarily the force reason. The fact that it's pushing on the wall's pushing back on it. The wall is causing the thing to stop and then move, get shot back. G and E are the same location. That'll be 0. At what point does it stop being 0 again?
H, because it's hitting friction again. H, because it's about to hit friction again.
So it's still 0 there, or not 0?
It'd be negative again, wouldn't it?
At H?
No, it would be 0, because that's the last moment it's on frictionless.
Right. And so now H2, its stopping point. So H,
It's slowing down, so it would be the opposite,
Yeah.
so positive.
and then I gets a little controversial here. I'm talking about that very moment that it stopped. The moment after I, it's 0. So it's still positive at this point, just incredibly tiny. So when we do our graph for acceleration, it should be getting, I guess it's coming from 0 to positive, so it's going to do something like this, and it's going to start coming back down. So we start out at 0, and then we go negative, and then we go to 0 again, and then negative again, then 0 again, and then positive at the very end. Now, in this presentation right here, we can immediately look and see that the regions where it is slowing down. Because all I have to do is look at velocity and acceleration. It is slowing down there. It is slowing down there. It is slowing down there. Those are the regions where it's slowing down. Because velocity and acceleration are opposite signs. The point where velocity is 0, but the acceleration is not, this would be a turning point. And there's something that exists on both sides. Probably better to see it as a turning point because velocity goes from positive to negative. I'll just leave it at terp. All right. Awesome.
I don't quite understand why between H and I, not including H, that the acceleration would be positive.
All right, so 2 ways of looking at this. Friction opposes whatever you're doing. It hates whatever you're doing. So the box is moving in this direction and friction's opposing that. The sign is purely about direction, so the friction is pushing on it in that direction or pulling on it in that direction. And so
it's pulling in a positive direction?
Yes.
Okay, all right, fair enough.
Other questions right now? Before we do the graph.
We're gonna do the graph on the test?
Yes. Oh, one other thing. Thanks for reminding me about that. On this type problem on the test, where I give you a scenario and you're going to have to do the plus negative 0 for the big 4 there, I will tell you no 2 of these will be identical the entire way across. So if, for example, you find yourself in a situation where you're going, position, displacement, I can't remember which is which, so why don't I just put down the same answer for both of them? What's going to happen is I just sort of got fed up with that, and you haven't done it. There's no reason. I don't want to take it out on you, but just letting you know, if you put down identical answers for these 2, that says I really don't know which one of them. I'm taking a guess at one, and I really have no clue about the other one. Whichever one gets you more points, I will give you credit for. I'll give you some credit for that one, and the other one I'll give you absolutely no credit for. So. Just letting you know they were all different. And also the other place where some people will do displacement velocity identical all the way across or velocity acceleration all the way across. And I will tell you the answer. You've missed something in that case. All right. So let's do the graph. Let's see, get rid of this part. Now when doing the graph, I have my guide right here. I've already gone through this. I know positive, negative, 0. Basically, it's going to kind of look like what I have down here, except throw some curves into it. It is more sophisticated than just that and throw a curve into it. But this is sort of a template at the moment. I've got a bunch of marks there, so I have A, B, C, D. So I have them marked off. Now, in reality, they should not be spaced equally, but this is just a sketch. So I'm okay with that. For some tests, I actually put down the letters on here, just so that to avoid those who missed the part where I say, make sure you put the letters on the graph. And other times I don't put them on there, so you can sort of space it the way you want to. All right, so blue, my axis is in blue here. I know it is negative until I get to C, so let me just mark down my zeros there. So that's 0 and 0 at the very end. It's negative in this region, so I'm just going to put a little dotted line, because this probably will need some adjustment. Yeah, and it's not, I know it will not look like that in the end. But this is just a quick and dirty, at least I've matched this. My velocity, first time. I'm going to put my back to you as I try to line these up. So put A there, B, C. I know velocity is positive 0 at F and I. And it is positive to start out with. And just a really crude sketch. All I've done right now is just match it to this display right here, where it's positive, 0, then negative, and then 0 again. And then acceleration. First time. Well, somehow that's what happens when they do it from the side. And acceleration, we start out at probably easier from here. So it's 0 from A to B, not including B. So I know it's 0 along here, not including B. This is just a placeholder. And then it is 0 from D to E. And then 0 from G to H. And then it is negative, negative, positive. So it's somehow negative, negative, positive, and I know it. All right. Again, all I've done is just match this. I have not gotten them consistent within themselves. Questions to hear before we start fine-tuning? All right, I know that this should be the slope of this graph right here. It's the derivative. So that means when my velocity is 0, my slope up here should be 0. So at point F, this should be peaking at F. So that should be a maximum right there. It's 0 at I, and so therefore this should be flatten out here. I should have a slope. So that's going to be, so I sort of start to narrow this down some. My slope is most positive to start with, and so it should be steepest here. It is most negative somewhere around here. Actually, it should be most negative at H. Wait, hold on just a second. Yeah, so H should be the steepest negative that I have, so let's sort of make that a little bit steeper there, and then it starts to level off again. I know that acceleration is the slope of velocity, and I know where acceleration is 0, so this should be flatlined here from A to B. It should be flatlined from D to E. It should be flatlined from G to H. It's negative from B to D, and so it should be sloping downwards there. It's negative from E to G, so again, it should be sloping downwards. And then positive here. Starting to add a little bit better definition to it. since my velocity is constant along this region right here, that means my slope is constant here. So from A to B, this should be a straight line. From D to E, it should be a straight line. From G to H, it should be a straight line. And so if it starts slowing down, that means my slope starts changing. And so what's going to happen here is I have to make another adjustment here, because if my slope starts getting smaller here, there's no way I'm going to connect up with that spot right there. So I need to make this steeper. Now, as I'm sort of dotting that in right there, I don't want any sharp points, and so the way I have it sort of have it coming in like that and then straightening out there, so I need to make some adjustment there. And then it is my velocity from C to, I somehow got off track there, let's see. That's negative. Oh, I'm off there. D to E is flat, not C to D. So I try to have straight lines here and then a curve the other spots. And then F is where it peaks. And so that's why there's these subtle adjustments throughout the whole thing. Something like that. Again, it is a sketch. Max?
Is there like somewhere in the book where you can practice that too?
Old tests. The graphing is relatively new. The old test will have problems, this part of the problems.
In that first graph, are you not missing your 0 at C?
We are. Okay, so that's why pencil worked better on this one. All right, so I need to hit 0 at that point. It needs to be curving downwards from B to C. So I draw a steep one right there. D should be flat line. To E, after G, it should be curved downwards until we actually peaking at F. G to H should be flat, so whatever position it's in at that point, let's flatten that out. And then H starts out steeper than it did, and so, but it needs to level off here. And suddenly we're off the chart here, so one thing I could do is, there we go. That's probably easier than adjusting the graph more. I think this still holds. And down here, I have sharp points, and so I have to need to deal with that one. Because it's not differentiable at these points right here, and it needs to be differentiable. And so it's just a matter of subtle curving here. B is not included, but it's really hard to draw the line so that it comes off of the axis just before B. So you do the best you can. Trying not to have a sharp point in there, to have a nice smooth curve. And then one last check is that acceleration is negative in this region, and so my curvature here should be curved downward, so there should be from B to D, it should have some sort of curve, negative curvature to it. E to G should have a negative curvature, and H to I should have a positive curvature. And that's the basic sketch. The three things I checked for. 1, are you consistent with this, with however you answered this part? 2, is this the slope of that graph? Is this the slope of that graph? And 3, are there any sharp points? That's what I checked for on the graph. Questions? As in, are there any?
When are we allowed to use graph paper on the test?
If you want, I have some graph paper, so I can scratch up some if you forget and you want some. Roberto?
There's a problem with E, F, and G are almost the same time in your timetable.
Wait.
E is just before it hits.
Right.
A fraction second after is F, absolute stop, and G start rebounding.
Well, it's already started rebounding before it gets to G. G and E are, oh, there we got the diagram. G and E are, at time E and at time G, the box is in the exact same spot.
Yeah, no, what I mean is that time, that delta T is very, very small compared to all the others.
Yeah, and one of the disadvantages of my putting down my letters here before I thought about the timing was that it really gets, some of the awkwardness that we ran into happened because of the times aren't really right.
Okay.
But again, I'm just looking for a sketch, so. Another approach to doing the exact same thing that might help is let's just make up a velocity to start with. Let's say it starts out at 20 meters per second, or whatever the appropriate units are. At B, it's going 20. Then it starts to slow down. By the time it gets to D, let's say it's going, let's put it next to the letter, 20, 20. Then let's say it's down at 10 by the time it gets to D. E, it should be going the same because there's no friction here. F is 0. This would be negative 10, and 0. It's not perfect, but it gives some idea, at least for acceleration. My change in velocity is 0, acceleration is 0. Change in velocity is negative, acceleration is negative. Acceleration 0, negative, negative, 0, positive. Probably better if I'd done, adding a little bit more accuracy here. 15, 15, 5, 5, negative 5, negative 5, 0. Since it lost 10 meters per second here, if it goes, let's say, half the way, it should lose the last 5 meters per second. All right, I know what you're thinking. You're going, oh, this stuff is just great. But where are the equations? Let's do some numbers. You got it. All right. So it all comes down to, is acceleration constant or not? If it is not constant, then you're probably going to be using some calculus. If it is constant, you could use calculus, but you don't need to. So we have what I refer to as K. Constant acceleration, kinematic equations. Sometimes I'll refer to them as the cake formulas, which means that they are the constant acceleration kinematic equation formulas. There's some redundancy there. Just go with it. Just like in high school, there was the CB building. The B stood for building. C for classroom. All right. It's like they ran out of energy at that point. It was language arts building, math science building, classroom building. So acceleration is dv dt. All right, so I just need confirmation here. Some of you have done integrals already. For those who are in Calc 2, you've done integrals at this point?
That's what we're doing.
Yeah,
We
we're
just
doing-
got into it.
Okay, so if I use the term integral, you're good. Ish. If I said antiderivative, would that make it feel better? Okay. From a physicist's point of view, antiderivative and integral, I will use them interchangeably. The math people might have some subtle difference there, but physicists don't care. So therefore, acceleration, dv, I forgot my vector symbol there. So acceleration times dt is equal to dv. Just multiply both sides times dt. Don't forget, dt is a quantity, it's just really small, but it is a quantity. And then we'll do antiderivatives. Well, I don't see a number here, so I'm not seeing anything, so it's an implied 1. In other words, the derivative of what will give us 1? Derivative of what will give us 1?
Constant.
Who?
Max.
Pardon?
What?
Derivative of x
Okay, or in this case, v.
of v.
So what happens here is that if I do the antiderivative of dv, what I end up with is a change in velocity. The antiderivative of dx is delta x. Now, you go from some initial x to some final x, it's just the change. You go from some initial velocity to some final velocity, it's just a change. Acceleration is a constant because that's what we're working with here, constant acceleration. So constants I don't need to worry about. And so this just becomes acceleration times change in time. Now we can do better than that. First, let's work on an assumption here. I can start the clock anytime I feel like it. Time is equal to 0 is as arbitrary as where you choose the origin to be. So what I'm going to do in deriving these formulas is I'm going to assume my initial time is 0. In other words, I start the clock at the beginning of the problem. Change in time is final time minus initial time, because that's what change always is, final whatever minus initial whatever. If I'm assuming that initial time is 0, that drops out. And so now I have only one time variable. So let's just call it time. And so this acceleration times change in time just simplifies down to acceleration times time. And that's going to be equal to the final velocity minus the initial velocity. And then putting it in a more standard form, VF is equal to VI plus AT. If you put delta T there, it's not wrong, it's just, I simplified it. And we can write it a slightly different way, is the fact that at some time t, we have some velocity. And so if we just assume, just like we just dropped the f from that, we could drop the f from here, and we could write this as v is equal to vi plus at. Sometimes I will put a subscript f, sometimes I will not. And that is just adding to the fun. So note, Vf is equal to V in this case. And also, Vi, sometimes, within the same problem, I'll write Vo or V0. Depends upon the way my mind's working at that moment when I'm writing it down. Awesome.
So is that the first kinematic equation?
That is the first constant acceleration kinematic equation. Now, unlike Newton's laws, Newton's first law is the same no matter where you go. Every physics textbook, Newton's first law is always the same. Not so with these. The constant acceleration equations, if you went up to somebody and talked about the first one, they might guess that this is the one you're talking about, because I think this is the first one that every textbook I've ever seen derives first, but it is not set in stone the way Newton's laws are. All right, so I know that velocity is the change in position with respect to time. For some reason, I'm on this S kick this semester, as opposed to X, which is what I've done almost every other semester. Doing this out, what we did before is that V dt is equal to ds. Now, V, we just derived a formula for that, so that's just Vi plus At dt is equal to ds. And now let's do some antiderivatives. The right-hand side, I have just the antiderivative of a differential, and so that's just change in S. Sorry, I did not clean out all the dog hair before I started. How much I've eaten. All right. And over here, I just distribute the dt, so this is the integral or antiderivative of vi dt plus the antiderivative of at dt. Just distributing. Vi is a constant, that's the initial velocity. And so I can just pull that out and just do an antiderivative of dt. So similar reasoning over there, we technically end up with vi delta t, but I'll just write it as vit. And I still wish they had not refused raising the board of fire. Plus, over here, acceleration is constant, because that's our premise. So acceleration will come out, and so we're doing the antiderivative of t dt. In other words, what will give us, what do we take the derivative of to get t?
T squared over 2.
T squared.
And so we get acceleration times t squared over 2. So writing that at a more reasonable height. we have the displacement or change in position is equal to VIT plus 1/2 AT squared. And we have the second one. Sometimes you'll see this in a slightly different form where they'll break that up into final position minus initial position is equal to VIT plus 1/2 AT squared. And then bringing SI over, and the F, sometimes they'll drop and you'll have S is equal to some initial position plus VIT plus 1/2 AT squared. Going back to what I talked about earlier when we did the sketch of the graph of the ball in the air, if acceleration is constant, then the position equation is a quadratic, as at most. Potentially linear if acceleration is 0. So let's write that over here. S is equal to S sub I plus VIT. Actually, I prefer the delta S version of it, so I'm going to put back in that form. Delta S is equal to VIT plus 1/2 AT squared. Right. Questions up to here?
These are the same as the Suvat equations, right?
Pardon?
Are these the same as the Suvat equations?
The same as the...
Maybe it's my mind.
No, I'm sorry, I'm just having trouble
Because
hearing.
we have the same thing, but it's like we call it the Suvat equations.
Oh, okay.
Yeah.
I'm not familiar with that term.
So yeah.
Suvat?
Yeah. SUVAT. So S is the displacement, U is initial velocity, V is final velocity, A is acceleration, and T
Oh.
is time.
Okay. No, I'm definitely not familiar with that. Which does bring up, V is generally what's used for velocity when you get to relativity and you're looking at relativistic velocities, you generally need another letter to represent velocity. U is often the common one used.
It's the same thing.
Okay. All right, and so if I'm plotting velocity versus time, I have some initial velocity here. If acceleration is constant, what is this graph going to look like? I'm seeing a number of people flatlining
It's
this.
gonna be linear.
It will be linear, but not necessarily flat.
Y equals X.
I mean, looking at it, it's a linear equation right there. Now, whether it slopes up or down depends upon the situation, but we'll just do slope up for right now. So this would be time t right there. This is the final velocity. And the slope here is the acceleration. So derivatives tell you slope, and I'm curious about for the Calc 2 people, what would the antiderivative tell you?
It's like, it depends, the antiderivative is the function for the area under the curve. But
All
if
right.
you take a definite integral, it's the actual area under that curve.
All right. I was going for area under the curve. I mean, there are other ways of answering it. And so what I want to look at here is, so if I do an antiderivative of velocity, that should give me displacement. So my displacement should be the area under the curve. And basically, we're going to derive that equation again. So I got a rectangle and a triangle. This rectangle has an area of VIT, so height of VI, width of T. My triangle has an area of 1/2 base times height, which is VF minus VI. And as we did over here, this is my change in velocity. That's just equal to acceleration times time. So this becomes 1/2 t times acceleration times time. And so what we end up with is VIT plus 1/2 AT squared. Shocking. Okay. Now, if I wanted to find the average value of velocity, the average value is defined as, I should be able to do the average velocity. I'm basically going to create another rectangle here. I want to create a rectangle that has the exact same area as the function does. That would be my average. So my average velocity times time should get me the exact same area. And if you'll notice that if the acceleration is constant, this average velocity here, well, it's got to be halfway between VI and VF. Let's grab that bit that I was trying right there. And this is just VI plus VF divided by 2. So my displacement is just my average velocity times time. And so we actually have another one of the Kate formulas. So VI plus VF divided by 2 times time. And 1 to go. Questions here? All right. We're going to do a small little interlude about something else, and then we're going to connect it back to this. Dot products. I don't think I talked about dot products last time. We'll deal with dot products in far more detail when we get to work and energy, but we do need to talk about dot products right now. There are 2 ways of multiplying vectors. One is called the dot product. This is also called a scalar product. Also called, I think in general, it's called an inner product. And the other way you do it is a cross product, also known as a vector product. Now, dot products are called scalar products. Well, first they're called dot products because the symbol that you use to indicate it is a dot. Anyone want to take a wild guess what symbol we use for this one?
Arrow.
Not quite.
The cross.
It will be, it's sort of the X cross, not the Christian cross. Yeah, because that would look too much like a plus sign. Dot products, can you guess what kind of answers they give? Only one of you? You just so believed in Precious that you figured if she answered, that was good enough for everybody?
Scalars.
Thank you, there we go. Austin didn't have as much faith in you. All right, here's a trickier one. What kind of answers do cross products give? You would think so. It actually produces pseudo-vectors or axial vectors, but they're still called vector products. There's a subtle difference between a pseudo-vector or an axial vector and actual vectors. The difference will have no bearing at all in this class. As if you get the high enough levels in physics, then the theorists care. I never did. All right, but I don't want to talk about those. I want to talk about these. So dot product. So if I have a vector A dot B, so I have 2 vectors here, vector A, vector B. What I want to know is how much of vector A is in the direction of B. Well, we do a projection. How much of A projects onto B? So this piece right here is the part that I care about. Cross products care about the other piece. Dot products care about this one. If this angle here is theta, then this little section right here is a cosine theta. And all a dot product is you're multiplying the parts that are in the same direction. So this becomes A cosine theta times B, or with a commutative property of multiplication, AB cosine theta. If instead we wanted to project onto A instead of onto B, so B dot A. So I have B coming down like this, I have A shooting off like that. Let's make A a little bit longer. The angle between them is theta. I want to know how much of B is in the direction of A, so I'm basically going to break it up into parts. This piece right here is the part of B that's in the same direction as A, and this is B times the cosine of theta. That's my right angle right there. And so the dot product here is B cosine theta times A, or, given the commutative property of multiplication, AB cosine theta. Questions for there? That's all we really need to know for this next piece. So if I have A dot product with itself, what would it be?
Would it just be the vector A? Or would it just be A?
Are you stopping there?
Yes.
There's more.
A squared.
Pardon?
Would it be squared?
It's the magnitude of the first one times the magnitude of the second one times the cosine of the angle between them. What is the angle between a vector and itself? Is that radians or degrees? And so since this is equal to 1, you're left with A squared. The vector symbol is gone. This is a scalar here. It is the magnitude squared. And I think now we're ready to derive the fourth one. So I'm going to take my acceleration, and since it's constant, it doesn't. The instantaneous acceleration and the average acceleration are the same thing. So this is just VF minus VI divided by time. And I'm going to take my average over there. I got my displacement is equal to VI plus, actually I'm going to keep that, or VF plus VI over 2 times time. And I'm going to multiply the left sides together and multiply the right sides. Since they're vectors, when I'm multiplying, I have to determine which kind of multiplication I want, and I want dot products. So on the left-hand side, I have A dot delta S. On the right-hand side, I have VF minus VI over time. Dot product, VF plus VI over 2 times time. Now the scalars here are just factors. You can take them in, take them out. They're not really involved in the mechanics of the dot product. So the time cancels out. I have time on top, time on bottom. The 2, I'm just going to multiply both sides by 2. So I have 2A dot S, delta S. And let's see if I can write that possibly neater. Sadly, that is neater. All right. And then I'm left with VF minus VI, dot product, VF plus VI. Now, a number of you probably already know what this is going to end up being, but I'm going to take it through the intermediate steps. Let's boil. So that's VF dot VF, outer plus VF dot VI, inner minus VI dot VF, VI dot VI. We talked about the commutative property of multiplication holds across a dot product. It does not across a cross product, but it does for a dot product. So those will cancel out. Again, if we were doing a cross product, we would not be able to cancel them out. However, the other two terms would go away. This is a vector cross product, dot product with itself, so this is just VF squared minus VI squared. Vector symbols are not written down here on purpose. And so, therefore, we have our last equation. VF squared equals VI squared plus 2A dot delta S. Some textbooks, I don't see it often, but I have seen some textbooks throw in a fifth equation, but it doesn't serve much in the way of purpose, so I generally leave it off. Yeah, the fifth one is you solve for VI in this equation, plug into here. Questions? Before we start manipulating stuff. I suspect Austin's the only one I'm blocking here, so it's just Austin.
No worries.
All right. Eventually I will move. Looks like there are some teachers who can write it this way. So dominantly right-handed. All right, so we have this 10-second journey. Car traveling along the line, so it's a one-dimensional problem. Initially going at 30 meters per second. It accelerates uniformly at 8 meters per second squared for 10 seconds. After the 10 seconds, what's the velocity at the 10-second mark? What's the displacement? At what time does it stop? And what is the distance traveled? Couple of key things here. The big clue that we're using cake formulas is the word accelerates uniformly. That's the code. Could also have said had constant acceleration, but that's just too boring. Uniform acceleration, same as constant. There are 5 basic quantities that we're working with here, and this is going to be true for this and the two-dimensional motion that we will get to in chapter 4 officially. There's displacement. Now you could break that up into initial and final position, but displacement, initial velocity, final velocity, acceleration, and time. If I know 3 of those, I know I can find the other 2. Now on a problem like this, 3 of the pieces of information are given straight in the problem. There are other problems where you'll have to read into it, you have to understand some of the language. We will get to that. So first off, what do we know?
initial velocity
is,
plus 30 meters per second.
all right. Now, the math people tell us I don't have to put a plus sign there, so why on earth would I put a plus sign there?
Because it's a vector.
Yeah.
What's the last thing? Time?
Time car stops. Now, if I had not put the plus sign, it would be more important for me to state that the initial velocity is 30 meters per second to indicate that it is positive and it's a velocity, not just a speed. All right, what else do we know?
The acceleration is -8 meters per second.
All right. And the third piece of information?
The time elapsed, 10 seconds.
Well, I see that the velocity initially and the acceleration initially are both opposite signs, so I know it's going to have to slow down. All right, so find the final velocity. Oh, we got an equation right there. Now, occasionally I have students who get into this position and they're going, I have no idea which equation to use. If in doubt, plug into all of them. One of two things are going to happen. One,
Get it right or get it wrong.
well, okay. I was thinking in slightly different space, but sure, that works too. You get an equation with only one variable and you go, oh, I can solve for that variable now. Hopefully it's one of those. Or two, you end up with two equations with two unknowns that are the same unknowns, and therefore you just solve them simultaneously. Use some of those algebra 2 skills. Or whatever algebra they stick it in now. Algebra 1? When do you do two variables solving simultaneously? That algebra 1?
I believe that's 2.
2? Okay. I guess if you're in the integrated math program, it could happen at any time. All right, so plugging into the first equation. Now, some of you can do this stuff in your sleep, and you can immediately jump into it. Matter of fact, some of you probably can pull out a calculator and come up with the answer, and just trust you're not going to make a careless error. I've seen enough people make careless errors, so I'm going, I can't believe that person missed this problem. I wonder what they typed in, but all I see is an answer, so I guess nothing. They get no credit. Show your work. So Ms. Sasson insists that you start out with writing down the equation, and that is good advice. I don't insist upon it like she does. However, it is good to start with the equation. Now, on the test, the equations will be on the first page, assuming that we are still face-to-face. And some people will mess this up because you've got this AT squared and this AT here, and sometimes people just nurse them in their minds, and suddenly this becomes VI plus AT squared, or VI plus 1/2 AT squared, which is basically this, but dropping the T there. Just please make sure you're writing the correct equation down. So that's going to be equal to 30 plus -8 times 10. I don't have to write units because I'm already starting out in decent units here. I'm dealing with meters and seconds. These are really nice units to work with, to the point where I will sometimes refer to them as nice units. These are nice units, and so I know what my answer is going to be. So this is 30 minus 80, -50 meters per second. And do insist that you have units at the end, even if you don't have them, keep track of them during the course of it. What does the negative mean?
That is going,
All right, somebody say it over here.
as in the opposite direction.
Okay. In other words, it turns around. Or reverses at some point. Next one, displacement. Well, I don't know, well actually I know this point, I know this one, so all I need is an equation that has delta S in it. Any one of these three will work. There's the vote for the third one, all right. So the displacement is going to be equal to VI plus VF over 2 times time. which is 30 plus negative 50 over 2 times 10. Doing the fancy math here, I believe that's negative 100 meters. Because it's negative 25 and 2 is negative 10, yeah. Okay. And then the time it stops. So at this point, it's a small change to the problem, but this is part of what is supposed to be understood. I didn't explicitly tell you a piece of information. Initial velocity is still a positive 30 meters per second. Acceleration is still negative 8 meters per second squared, but we don't know time anymore. But we do know final velocity. So a simple example of, it's implied when I say stop that the velocity is 0. And so now we're dealing with this, we're solving for time, and so we need an equation that does not have displacement in it, but does have time in it, and we're back at the first equation again. Sorry, you were pointing, I should have given you a chance, Marisol. And so to solve for this one, I'm going to get cocky and just plug straight into the formula. 0 is equal to 30 plus negative 8 times time. Now, one of the reasons why I am plugging in here as opposed to just going straight to the calculator is I want to make sure that my signs work. Because if I end up with a negative time, that should tell me either I made a mistake or it happened in the past. Or it's an impossible problem, potentially, given whatever the boundary conditions are. So I subtract, so I get negative 30 is negative 8t divided by negative 8. And so time becomes 38ths, which is, it does end up being a positive number, which makes sense. And now the distance traveled. This is not just the magnitude of the displacement. Physically, what's going on is the car starts in some spot traveling in the positive direction. It moves in the positive direction, stops, turns around, and goes back. Ends up 100 meters on the negative side of the starting point. If I sketch it out, goes out, comes back, ends up over here, where, assuming that's positive, and from here to here is 100 meters. So I need to figure out how far out did it go before it's turned around. There are many ways of doing this one, but I know I'm going from 30 to 0 in 3.75 seconds. Seems like the third equation is the simplest here. My average velocity is 15 meters per second for 3.75 seconds, so my displacement, using that equation right there, becomes 15 meters per second times 3.75 seconds. Is it 56.25?
Yes.
Meters. That's not our final answer. All we've done is figured out that it goes 56.25 meters before it stops. And then it heads back. It has to travel at 56.25 meters back to the starting point and then an additional 100 meters in the back. So the total distance traveled, you got the 100 here, you have the 56.25 to stop, 56.25 back to its starting point. There are other ways of getting to the exact same answer. So just, if you've got a way that works better for you, go for it. So 212.5 meters is the distance traveled. Unless there's a careless error somewhere. Which I'm not opposed to doing occasionally. Assuming Marisol's taking a picture.
I am taking pictures.
Good.
So,
Tom?
how did you know, other than just, like, looking at the distance traveled, the little graph you made?
Right.
the picture you made, how did you know that it traveled 56.25 meters again?
All right, so I know that the distance, the displacement is average velocity times time. And distance is the magnitude of displacement as long as I don't turn around. So if I just go in one direction, then my displacement and distance have the same magnitude. So I'm going to present it slightly differently and take this slide. So time in seconds and velocity in meters per second. So 0, 1, 2, 3, 4, 5, 6, 7. So I start out going 30 meters per second, and my acceleration is negative 8 meters per second squared. That means that my acceleration is negative 8 meters per second, which means my velocity will change negative 8 meters per second every second. So 30, then 22, 14, 6, negative 2, negative 10, and so on. And I should end up doing it this way. It's a lot longer than the algebra way. Doing this way, I should end up at negative 50 by the time I get to here. I know that I can't go from positive to negative without going through 0. So somewhere in here, I stop to turn around. And since going from here to here, from 6 to 0 is 3/4 of the way. This would be 3 3/4 seconds. So now for that 3.75 seconds, my average velocity is, well, I just averaged the first and the last, so I averaged the 30 and the 0. 15. So on average, I go 15 meters per second for 3.75 seconds, so just multiply those. Does that answer your question? Okay. That's, here I did it more formally. I found the average velocity this way, which is in essence what I just did there. Max?
Whenever you found the displacement, you used negative 15 meters per second for the final velocity. So why did you have 0 meters per second?
Because at this point, when I asked the time it stopped, well, I'm not dealing with the full 10 seconds. Basically, it's a slightly different problem.
Okay.
Other questions at the moment? All right, ball in the air. I threw a ball straight up at initially, although I think it's implied, I don't have to say initially, if I throw it implies that at the point when I release it. At, let's just say I'm a major league player, so let's, 45 meters per second. Was it in the mid-90s? Miles per hour. How high up does it go? So now I have a problem where I've given you one number, and we need 3. One other piece of information that is implied here, but I probably should say it explicitly. Assume I am standing on the surface of the earth. Now, most likely there will be a problem in the first test that does not take place on earth, and you need to adjust for that. We'll talk about where that shows up. So I got my basic quantities here, got my displacement, I have initial velocity, I have final velocity, I have acceleration and time. What is the one piece of information that we are explicitly given in the problem?
The acceleration is G.
That we are given explicitly in the problem. Yep. You're jumping ahead. Positive 45 or negative 45?
Positive.
What assumption did you just make?
The origin.
If you can choose up to be negative if you want to, there's absolutely no problem with that. It does not change the answer. Also implied, how high up does it go? This is from point of release. Since I did not tell you how far the hand was above the ground when it was released. All right, so we have our one piece of information here that's explicitly given. There are 2 others that are implied. So let's first, not wanting to delay Roberto, but let's do that one, the second one. What's the other piece of information that we were given that is not dependent upon the Earth?
The final velocity is 0.
Yes. And so that goes along with how high up does it go. If it is not 0, if it's still a positive velocity, given our convention there, if it's a positive velocity at the peak, that means it's still moving up. If it's negative velocity at the peak, that means it was somewhere higher up and then it's on its way down. So this is 0 meters per second, and this is implied in the problem. And the other piece of information that should be understood in the problem, as Roberto said, acceleration.
Gravity.
Acceleration due to gravity, because we are on Earth. Once the ball has been released, the only force acting on it is its weight. And so if the only force acting on it is the force due to gravity, which is weight, then the acceleration is the acceleration of gravity for that planet. Ish. The acceleration due to gravity is not constant. But it's close enough, often enough, that we pretend it is. So we're going to be using the cake formulas as long as this object doesn't get too far from the surface of the Earth. The acceleration due to gravity is a special symbol. Acceleration due to gravity. Is G. Little g. Do not use big G. That is the gravitational constant. That is something different. G is a positive number, unless you somehow have anti-gravity going. Now our acceleration might be negative, but G itself is a positive number. In Winston-Salem, actually where we are right now, G is 9.798 meters per second squared. Matter of fact, they did a study. They've done several different studies trying to find the acceleration due to gravity. They did one with a plane flying overhead, and that data is available online if you can find it and decipher it. But in I think it was the 70s, the first time they did it, and actually in daylight when you could see it, basically about the same elevation that we are right now, in the median, Silas Creek, right in front of whatever road that is that cuts in right over there, that's where the spike was. So, Rome, I'm going off memory on this one, Rome, 9.8 meters per second squared. And I don't have, yeah, it's at home, nuts. Death Valley is the lowest that I could find. That was 9.72, somewhere around there. Mexico City was one of the highest that I saw. So the main point here is that it's not constant. However, as long as we're near the surface of the Earth, it's relatively constant. It's, you know, we're adjusting here. There's just a small little swing of maybe about 4 or 5%, depending upon where you are on Earth. So if for an Earth problem, 9.8 works. Negative because we said up was positive, and acceleration due to gravity is always down towards the planet. Mars, I think, is 3.7. Venus is 8.9 meters per second squared. On average, Jupiter is 20, somewhere in the mid-20s meters per second squared. The Moon, about 1.6, 1.7 meters per second squared. So now we have enough information to figure out how high up does it go. So we're looking for displacement. Seems like the fourth one is the one to use. EF squared equals VI squared plus 2A dot delta S. We are dealing with a dot product here. My displacement is going to be positive or negative. I throw it into the air. Will my displacement, when I answer this question, will that be positive or negative?
Positive.
I hope so. If I throw something in the air, I do expect it to go up. And we said up was positive. Acceleration is negative, so it's in the opposite direction. In essence, I'm going to multiply 9.8 times my displacement, and then the angle between them is 180 degrees, which gives me the negative sign, or I just multiply negative 9.8 times delta S. If it's a one-dimensional problem, I just treat the numbers like this and plug them straight in. So I have 0 equals 45 squared plus 2 times negative 9.8 times delta S. And so I get, I had to pick a number that I can't square in my head. What is it?
Negative 2025. I'm sorry, 2025, not negative. 2025, it's not a negative.
2025? When I take it over to the left side, it will
When
be.
you take it over, you're negative.
Equals negative 19.6 times delta S. Divide by negative 19.6. I am keeping track of the negative signs because if I end up with a negative answer for my displacement, then something has gone wrong. Treat the minus signs as the canary in the coal mine. So I end up with delta S being
103, how many decimal places do we need to take out?
2.
103.32. Two decimal places? Meters.
Thank you. And the answer. How much time does it take? Which equation would you use to figure out the time? Okay. Now that we have that, so 103.32 equals 45 plus 0 divided by 2 times time. So my time will be 103.32 divided by 22.5. Which is 4.6 7, 3, 16689.
4.592.
592. Seconds. Can't believe I missed that. So now, the fun ones begin. I still want to use those, so I'll keep those up there. Maybe I should move the camera back next time and get more of the board. We'll keep that. All right. At what time is the ball 60 meters above point of release? The ball is going to be thrown up in the air. It's going to go up a little over 103 meters. It's going to come back down. I know that I should have two answers for this question, because it's going to hit it on the way up, it's going to hit it on the way down. The average of those two answers better be somewhere around 4.592. So I have some clues already before I even begin. Final velocity is not zero anymore, because we are now dealing with a point that's not at the peak. I do have displacement. It is positive 60 meters because the question is above the point of release, and we said up was positive. And I'm solving for time. Which equation? Well, since I don't know what the velocity is, the second one seems good. So I have 60 equals 45 times t plus 1/2 negative 9.8 t squared. That is the problem. Just straight plug in. 60 equals 45t minus 4.9 t squared. This is the point where some of students in the past in this course have shown their real weakness in algebra. Please show your work. How do I solve this?
Difference of two squares.
Difference of squares?
Oh, wait, no, never mind.
Term and a constant term.
Quadratic equation.
It is a quadratic equation, so how would I solve it?
So,
Quadratic formula.
Yeah, that's it. I knew that's what you meant, but. Now, to use the quadratic formula, what form do we need to put this in? Oh, okay, I'll buy that. Now, whether you put everything on the left side or the right side is up to you. This is my own childhood scars. I like the quadratic term, the t squared term, to be positive, so I'm moving everything over to the left side. 4.9 t squared minus 45t plus 60 equals 0. And so, (45) plus or minus the square root of negative 45 quantity squared minus 4 times 4.9 times 60 divided by 2 times 4.9. I'm trying desperately for Pop Goes the Weasel not to run through my head. And I apologize if now it's running through your head. If you don't know the reference, good for you. And so I get 45 plus or minus the square root of this thing right here. And I'm thinking, let's see, so that's roughly 1200. So somewhere around the square root of 800. Probably a little bit more. Let's go with 834.7.
849.
849 divided by 9.8. If we do 45 divided by 9.8, just ignore the square root part, that should give us 4.592. All right, so at this point, our two answers are
Negative 24.55.
something's wrong. Because we should have two positive answers.
We have a
Yeah.
positive 7.5.
No, it's not possible, yeah, 900, square root of 900,
Yeah, so this would just be under 30. Did you forget the square root?
Yeah.
Okay. All right, so what are the two numbers?
One of them is, positive 7.57.
Or and.
The other number is, 1.62.
Ah, because 4 minus 3 is 1, not 2. All right. Seconds. Two answers. Right. At this point, so Tuesday, 9/8. Master set 2 is due. We're still gonna cover some stuff next week, but these should be enough for you to get started on master set 2. And so you would go into Blackboard under assignments, under chapter 2, and there'll be the homework problems from the textbook, and then there'll be something where master set is in the title. It is 8 problems, some have multiple parts.
Can you email those dates?
Pardon?
Could you email those dates to us?
In theory. I figured I'd just write them down once and then, people hand them in, I go, oh, okay, that's the due date, so, but we can make it more formal. Let's see, so 9/1, we got the quiz, so that's next week, and then 9/8, master set 2. If I'm off by date, because I looked at the calendar wrong, then just adjust, it's the Tuesday nearest that.
next Tuesday.
So next Tuesday, a week from today, you have the quiz on chapter 1, those are the textbook problems. I'm gonna take 2 of those problems, change the numbers, and that's the quiz. And then the week after that, master set for chapter 2 is due.
This is the stuff we did today with chapter 2.
Pardon?
The stuff we did today with chapter 2.
Yes,
Okay, quiz number 1, next Tuesday.
yes. Yeah, quiz chapter 1 next Tuesday, master set for chapter 2 the following Tuesday.
All these chapters are in our book too, right?
Pardon?
All these chapters are in our book too, right?
All these what?
The chapters are from our book, right?
Yes, the chapter 1, these are the ones, if you, under assignments in Blackboard, chapter 1, the document there, with the textbook problems that I'm assigning, as well as the solutions.
I'm gonna look at the video.
But they're in the book, so you don't want to do the solution because it's within the book?
The problems are from the book, I don't have the separate documents, so if, when you open up the document, the problems assigned will be at the very top, but then the solutions are right there, so. Shielded.
I just don't like to look at the solutions.
Yeah,
It's
Shield your eyes. Pardon? There's no, separate chapter 1 or 3.
That was actually about to be my question.
And I think chapter 31 is yeah. That's why I said calculation. Pardon?
Is master set posted to Blackboard, or the master set to posted to Blackboard?
No, master set we will hand into me.
Where do we find it though?
Under, go to Blackboard under assignments.
Chapter 1 homework.
Go to chapter 2.
So it would be. Oh, okay.
Master set.
Gotcha.
Do we need to have the same, material? Do we have to, like me and my partner, do we have to guess the same material?
No, you don't. And if you wish to put a comment on the side of, he's a fool, I can't believe he said it was such and such thing.
So I have a significant figures question for the lab this
Okay.
Thursday. Yeah.
You
I know
can
it's your
make
favorite.
me, understand why you think you need more. All right.
Yes, yes,
Right on.
absolutely. So going between, this table into this table, I just wanted to make sure the standard deviation should have the same number of significant figures as the least number of significant figures measured in the data, correct? Does that make sense? So like, for example, right here, this one would have 4 significant figures for the diameter because these were measured out to 4 significant figures.
It actually, this should go out to 2 decimal places because that goes out to 2 decimal
Okay,
places.
gotcha.
There was a bunch of additional on there.
Gotcha.
And this would go out to, since that's in millimeters, and that's in millimeters, this would go out to 1 decimal place.
1 decimal place.
Yeah.
And just out of curiosity, so that, okay.
In terms of significant figures.
And the only reason that it does, okay, because they're not being multiplied or divided, they're just being added and then
Yeah.
divided by an exact number.
Yeah. There is a situation, which I ran into a couple of years ago, where there's 2 different ways of doing it, taking significant figures into account and actually coming out with a different number of significant figures in the end, depending on how you went about it, which is one of the reasons why after the first lab, I don't care.
Okay. And, yeah, I'm sorry, I'm gonna bore you with some more, but, when I then figure out the number of significant figures in the standard deviation, would that then be 3 significant figures? Because then
The
you're
standard
taking
deviation-
the average
All right, so you've got,
and the individual samples over the
Yeah.
number of samples.
4, and you square it, so there'd be 4 under the radical, so you'd end up with 4, so for standard deviation, you should have, it should be based upon the number of significant figures, not the decimal places, so it would be 4 significant figures for standard
Assuming
deviation
that-
for the,
For the
assuming,
diameter.
because those are all 4.
Right, so this one would end up being 3 because the least accurate would then be 3.
Yes, I would agree with that.
And so then these would be, what, 2? Is that
Uh,
trailing 0 significance?
So the average
Would be 2.
would be 2 there.
No, 1. Right? Cause that.
Oh. No, it's still 2 decimal places, because you add them up, to find the average, you would add them up.
Well, yeah, but then for the for the standard deviation rather, for the.
Oh.
Balance, would that
Yeah.
end up being?
Yeah, this is what, yeah, I think that.
Cause I had
that's what you're right.
I had some to do with all these, like the sig figs, but chemistry, it's not as, like, we did standard deviation like 4 times off the top of my head.
Okay.
And sig figs weren't even factored into it. And so, but the uncertainty would be the same, it should be the same as the standard deviation.
Yes,
Okay. Okay.
that I'm good with.
Okay, so the way I'm gonna do it is just, the least significant or the data point with the least significant figures in that category will be the significant figures for the standard deviation and for the uncertainty. Does that
I'll
make
buy
sense?
it, I'll buy it.
Okay. All right, and then for this, this is gonna, when I'm doing this is gonna be the number that I'm using, is this gonna be the average plus or minus the uncertainty?
Yes.
Okay, okay. got it.
Average circumference divided by average diameter, plus or minus,
The uncertainty for,
that propagates through.
that propagates through, so I don't even have to mess with the dividing.
No, the uncertainty, so the uncertainty is gonna,
uncertainty.
so you'll do circumference divided by diameter, plus or minus, circumference divided by diameter, times the square root of
The,
uncertainty, the relative uncertainty is added in quadrature.
okay, all right,
Okay.
awesome. All right, thank you. Sorry for,
No.
boring you to tears.
No, it's just, you know, and I'm gonna forget, they say the same thing about having children,
Mm-hmm.
that, you forget about the pain when you decide to have the second one.
Can I ask you a couple questions?
Let's